Ahoy Captain, and welcome to this tool tutorial for the Shore Power Terminal tool. Lots of tools and also lots of disclaimers and assumptions today, because this will be a pretty complicated topic. We will tell you everything there is to know on how the terminal tool works, not just the web tool itself but also the Excel, what our assumptions on the models are, how we do the calculations and the formulas, etc, etc. Feel free to skip to the fun parts that are applicable to your situation, and as always, feel free to reach out when you have any need for help or clarifications at all by contacting the help desk. Before we dive in, a few disclaimers from our part. As always, this tool is an estimate. Especially for this one, this will be extremely difficult to pinpoint for each case specifically, so we make generalized assumptions and give you all the tools you need in order to perfect that estimate for your situation. However, the variables for each ship and each type, well, in fact, we assume a single ship as a reference for all ships for this case, but of course we know that every ship is unique. So please keep that in mind while making assumptions for your shore power infrastructure, especially onshore. And then finally, it is very much subject to change. Thanks to your feedback that we are constantly receiving, we will get more information on what's useful to you and what you can use moving on towards the future. And I myself will also highlight some of the features that we are working on, which will probably not affect the underlying assumptions per se, but it will mean that this video, when you're watching it, might be a slightly different version of the model and the web tool that you are currently using. In either case, we have a method to help you with anything, also these kinds of questions, and that is simply to reach out and contact the help desk in order to make your life easier and get the clarifications you need to make your business case for your onshore and or offshore or maritime shore power related equipment, infrastructure, anything you want. Enough with all the assumptions, disclaimers, etc. Let's dive into the fun part and start with the premium web tool. And here we have the Shore Power Terminal tool. As I said, it's the premium version that we have here, so if you're using a freemium version, there might be some features that you cannot use. Either way, most of it will still be here. So let's scroll down a bit and start from top to bottom. So what we're asking you first is, of course, to select a ship type and a subtype, or actually what we call it, a category. So that's classification of ships, and within each category we have different kinds of ship types. So for example, if we go to tanker, then we see that we have general liquid, crude oil, chemical and oil products tanker. We also make some assumptions based on the ship category and type. And of course, in the premium model, you can change all the variables we want, but right now we take types in order to preload all the information, including information on the average engine loads, power demands, etc. We're gonna go for a container ship. That's always a nice example because they carry their own CMS system, cable management system. And the terminal length itself mostly impacts whether or not you want to use high voltage cables and or transformers. I'm just going to leave it at 200 for now, and I'm going to show you how that impacts everything. So what are the most important parameters according to, well, our clients? That's of course how much money do we spend in terms of CAPEX, the payback required. Right now we simply take 7 years payback period for the investment, but of course that's up to you. And then we calculate the break-even price of the kilowatt hour. That means that for the shore side, which price is needed in order to get the investment back within 7 years, and from the ship side, which price is needed to get the investment back within 7 years. However, the shore needs to be more than that in order to make a profit, and the ship needs to be less than that price in order to, save on the investments. So it needs to be in between those values. Right now it needs to be higher than 18 cents and lower than 29 cents, which means that anything between that value is a viable business case. But once we start tweaking with all the parameters, that break-even point might change. This, however, in our estimate is the most impacting parameter for determining whether or not you have a viable business case, because if both shore and ship have a proper break-even price, then of course everybody should be happy. So I'm gonna show you 1, 2, 3 and 4, that is shore, ship, CAPEX and business case. So shore itself is everything shore related, infrastructure, etc. Ship itself is everything ship related. With those we can calculate CAPEX cost, which is simply a bunch of line items based on those input parameters. And then finally the business case, which is the OPEX side of everything, which determines all the costs, the running costs, fuel, electricity, maintenance, spares, and of course EU ETS and FuelEU. And we'll just go from left to right, and then I'll show you all the relationships, the exact calculations, and how it's done. I'll show you in the Excel model later on. First we go to shore. As you can see here, this is a summary or an electrical diagram, an assumption. These are the assumptions that we make in order to determine the technical properties of the system. So as you can see, we can change rated power of the ship. 18,500 kilowatts is stated here, which is quite a lot, because that means that all the power needs to be rated up to that level. I'm gonna change it to right now 5,000, see how that would impact the... that's good, because it leaves us with a wider range of what's needed. Ship main voltage, frequency all stays the same. We're gonna need a converter, but as you can see here, if we don't need a converter for whatever reason, then of course that will impact the costs and infrastructure costs quite severely. And as you will notice, if we for example change grid frequency to 60, same as the ship, then automatically that assumption there is also changed. But you can see we make some assumptions, and in the Excel model I'll show you how those all relate. But here we can input everything there is to know for the shore side, and then the costs based on the amount of kilowatt hours, length of the cable, voltages, etc. are then calculated in CAPEX. Not much to say here. In the future we will of course add things like solar panels, backup diesel generators, battery systems. That can all be included also on the shore side of things, but it's also very much dependent on a case-by-case basis. So typically at the moment we simply use a consultancy or tailor-made projects in order to specify it for you, but we'll use that knowledge in the future to also add it here to make you a better estimate of the business case. Then going to the ship, this is why we had the 18.5 megawatt of energy or rated power. We're taking the Algeciras as a base case, pretty large container ship. We'll just go from top to bottom, as this already has a lot of information, and I'll show you all the things that you can change and how that impacts the business case. So first, if needed, we can change of course the ship type to, for example, feeder. That will definitely impact everything, but if we go back, then also the changes we made here will be overridden. Work from left to right there. I'm gonna go back and use the Algeciras. Let's see, container ship as our base case, and I'm gonna change this back to 5,000. And what I'm basically saying here is that with 5,000 kilowatts, we should be able to serve all the average ships that we need. So the end of life 2040, as you can see here, shore power already. That means that if we cross that off, the checkbox, then we simply assume no CAPEX is needed for the ship, as it already has shore power, and that of course definitely make things better. And in this case, the break-even price should correlate with the regular fossil fuel price generally. The reason why this is so high here, you might wonder if, most ship owners assume lower, is that this includes everything, including maintenance, compliance costs, etc. I'll show you that in the business case or OPEX. The end of life, of course, we can adjust it here as well, but it's better viewable in the business case. We have a nice slider over there, so easier to do. And then, very important, the amount of sailing days and the amount of shore power days we have per year. How does this work? Well, we have a certain set of sailing days. Let's make it, for example, 300. There we go. And then you can see that this does not go all the way up to 365, but that's because we assume there could also be some days in the year that you're not on shore power, that you're simply idle mooring regularly. So then we take about 80% of the remainder of the days. So we have 365 days a year, sailing days, and the rest is idling and mooring, of which we normally assume 80% to be shore power. That's fine. As you can see, we can change it all on the fly. Then shore power equipment. This one's very important, especially a rated power. That determines most of the CAPEX and some of the regulations, especially a low voltage shore connection system or a high voltage shore connection system. There you go. Anything below 1 megawatt typically is low voltage, and everything above is high voltage. Of course, it also depends on the voltage itself, but that's how it's stated in the standards. Main voltage and frequency mostly impact whether or not you need a transformer and or converter on shore. The drivetrain itself, well, we assume some assumptions, of course, but that mostly relates to thinking about how to connect it to your switchboard if you want to have lots of power. And your switchboard, we'll discuss that later, is one of the most important aspects when it comes to shore power in general. We can choose one or two connection panels. So do we want to have a starboard connection or a port side only, or both connections? Of course, you can do more, I guess, but more should not be needed. And then that automatically translates into whether or not you need switchboard modifications or a transformer on board, depending on. These are the most defining parameters for all shore power equipment and also correlate mostly to the costs, as we will see later. Then the power demand itself, that mostly correlates to, of course, the OPEX. How much fuel do we need, or, well, could we save in this particular scenario? So the aux power of the engines is 18,500, as you can see here. And even if, as we've seen, we've overwritten the rated power of the equipment, we still need to be very careful about what's here. We have taken those separately, so the auxiliary power of the ship and the rated power, because we've noticed that in a lot of cases the rated power needed for the equipment is not the same, especially not onshore or shore, as for the general power demand of a ship in idle moored. So if we have an engine of 18.5 megawatts, typically for diesel electric propulsion for these container ships to also include a lot of reefer, then we have with a 40% average engine load about 7.308 kilowatts resulting average power. So what I'm going to do, 39.5, so what I'm going to do is make it 25 as such, resulting in an average power demand of slightly below 5%. Furthermore, it's good to note that we include a parasitic load of the engine. What does it mean? Typically, especially larger vessels, they require power to keep the engine running. Think cooling water, pumps, fuel pumps, fans in the engine room, everything you need in order to keep everything running. So that's the parasitic load of the engine, and that is discounted in this particular model with any energetic losses from the shore power equipment. So for example, parasitic load engine of 5%, I'm gonna make this 50 to really show you the difference. Here we see that while the engine requires or results in an average power of 4.6 megawatts for the entire ship, if we are connected to shore power, then we see that we only need about 2.3 megawatts of truly used power, electrical power coming from the shore. What I have seen, depending on the ship size, is that it's either negligible for smaller ships, but especially larger ships, typical ships that have quite some spinning reserve, could actually have indeed almost 40-50% of parasitic load from the engine. I'm gonna put this back to no, we're gonna keep it at 0%. That's basically the most conservative case in most cases, but I guess it depends on which side you're looking from. Moving on to fuel consumption. Here we can see we have fuel consumption. This is definitely something that we are going to improve in. We want to be able to more easily provide you with different fuel solutions, auxiliary and main fuel. It is, even for shore power cases, important that you get the main fuel type and fuel consumption over the year correct. Why? Because that value is needed to calculate FuelEU penalties, and that really impacts these kinds of ship types. So that can be very important to your business. Either way, so here you can see this is the fuel consumption per year, and we can change the average sailing and idle moored fuel consumption if needed. It depends on the fuel whether or not it's taking kilograms or liters as a metric to calculate stuff. We're also going to improve there, but in this case, auxiliary fuel type, MDO. So for example, if we change this incredibly accurate value from let's say 29 4000, so 33, yep, there we go. So if we change that to for example a little bit more kilograms consumed per day, 30 tons, then you can see that automatically impacts the auxiliary fuel consumption. Should suffice. This is the fuel consumption that's also used for the calculations in FuelEU. So this is an average day, and then subsequently this is done for the entire year. and it also impacts the OPEX calculator. If we change these values, everything else is changed. Then going to the electrical side of things, as you can see here, we have rated power, voltage and frequency as per, well, everything. These are basically assumptions on how we assume the ship switchboard is operating. In this case, for a very large ship, we most likely have a high voltage switchboard to which we connect for operational shore power. Then we have a medium voltage switchboard of 440 or similar volts. And then we have a low voltage switchboard, 200, 220, 230 for all the crew appliances, etc. So that's how I assume. If you have or if you need something else, then always feel free to reach out if anything differs from yours. The general arrangement, well, this is simply a nice picture. Doesn't really correlate with your vessel per se, but what we do is we determine again the amount of connection panels and bulkhead penetrations. That mostly impacts the refit costs, not just time and man hours required, but also for connection panels, the CAPEX equipment costs. And then finally, sockets and plugs. And for a container ship, that's a nice one, because a container ship needs to have its own cable management system on board as per IEC 8080-005. And here we can see some of the main or key parameters as per the standards. Of course, you need to dive into the standards for all the details, but this is a summary of what's most important for the ship and therefore also the shore, because the socket and the plug arrangement, of course, has to align. Well, makes sense, but still, it's quite a topic. That's it for the ship side, or at least what you can fill in all the details. Let's move on to the CAPEX side, and as you can see here, these are all the line items and all the different items that we assume are required for the modification. We can switch them, of course, on and off specific items, and in the two sections, that is the shore side infrastructure and the ship side, we can play with the independent sections, well, individually. So for example, if we're not going to include design and engineering, that's reduced from the CAPEX cost, but in this case you can see that well, the man-hour costs are dwarfed by the equipment costs, equipment and procurement costs. So I'm going to leave those on. If you do show more here, if we can leave these out, then of course it becomes more comprehensible. But if we select everything, that means design and engineering, the equipment, the installation of everything itself, the commissioning and any class or certification costs, then you can see that for each of those aspects we have different line items that we assume to be applicable to that specific section, and you can change that individually here. For example, if we here have a transformer 1 down, 1.2 million for 5 megawatts, seems to be a lot, but could be in a proper range. We can always, once we have a good budget quote, change the values here, and then everything else will automatically be changed as well. The same applies to the ship. That is basically exactly the same, except for the fact, of course, all the line items are different. And here we see that the ship CMS is included here on the ship side, because, well, it's a ship CMS for the container ship. If it's not, then it's included on the shore side. Always keep an eye out for those. But again, similar approach, all the different line items and modifications needed for the ship itself, and everything can be customizable as per your desires. This is not just here in the web tool itself, but that's also included in the Excel model, which I will show you later on. So basically the CAPEX side is simply the result of the input from shore and ship side, and then we can play around and see what we will and will not include in the total costs of ownership. And again, if we go to the ship side and implement shore power already, then we assume all the CAPEX cost for the ship is 0. So then it's all discounted. We're not going to do that for the moment. That's no fun, especially not for making a business case. And that is, of course, the biggest fun part of them all. The biggest fun part. Oh man, what am I saying? Now, the business case, if we go there, is where you could say the magic happens. We transform the technical shore and ship side of things into a total costs, CAPEX, and then given the OPEX side of things, that is fuel, maintenance, financing, etc., etc., then we can make a payback period, as we can see here. Well, this almost looks too good to be true, so let's have a closer look and dive in, and then I'll keep the break-even point there just at the right hand side. So one of the first things you'll notice is that we can change the end of life of the both the onshore and the ship side of things. These are decoupled in two ways. One, the amount of days that the ship will be moored is not the same as the amount of days that the shoreside installation will provide power. So we're indirectly assuming the shoreside installation will have more ships to serve that are similar to, in this case, the Al Jazeera's. And as you can see, we take a different end of life for both of the two systems. So let's see, 2040 seems like a good end of life for this system. Maybe 2050. Well, we're just gonna do 2050. 25 years, yeah, that could be, well, that could be for such an installation. Yeah, it's a lot of profit. Yeah, but we're also gonna do 20 years. Easier also for the eyes. So this already looks quite well, so let's have a look into as to why. Here we can see that the amount of shore infra supply days, as I said, is different than the amount of shore power days. Let's see, yeah, shore power 52 days a year, shore power supply days 183. So we're more or less assuming 3 of these types of vessels year round, or well, that is the amount. But it could also be that this installation is well, having a lot less ships, and maybe the cost price for electricity is a bit higher. And the electricity price is a bit lower. Now we're gonna do this a little bit higher, so we're gonna make it more nuanced, and then a little bit higher of yeah, electricity price. 20 cents per kilowatt hour, that's very cheap for, I'd say, a ship. Doable, depends on the terminal, what kind of ships you have. Cost price of 17 cents per kilowatt hour. Of course, this is all excluding taxes. Well, that's high, I'd say. What we can also do is add subsidies for the infrastructure on shore, and then you can see that the CAPEX costs are reduced up to a maximum of 100%. And we also limit it to the maximum CAPEX in this case, so that you don't get really more money than, well, you deserve. Another thing that we have included is shoreside and shipside financing, so that you can, well, in this case we of course need to bring back the non-subsidy. So in this case you can actually transfer the CAPEX into an OPEX. It's easier if I show it with the ship side, because there we have a more detailed breakdown of all the OPEX costs. Before we do that, quickly showing you what we have for the ship. So we compare both fuel and electricity for conventional and the shore power case. Financing, which I'll show you. Maintenance consumable, standardly we leave it out. EU ETS and FuelEU, up until we get the costs per day, and then multiply that with the amount of days we've already included to gain an average costs per day for the entire year. And here we can see the savings. So in this case we actually pay more for the fuel, but we save a lot for compliance, and because we leave maintenance and consumables out. But in this case it's also fairly low compared to the rest. We can see that most of the savings come from FuelEU and not necessarily fuel price or electricity price. And now if we include maintenance, for example, maintenance financing, so then we can transfer CAPEX all the way to OPEX, and then we don't have cash out, but we have a daily expense, which is our payment and interest, which you can see here. We can also change, of course, the different rates, interest rates, and the amount of time that it takes to pay back the loan, in order to get a proper grips on what that would mean, a leasing or a financing structure for this particular operation. If we leave financing out, however, what else is there to say? We can have a look at the reporting year to see the different cost components for every year. So you can see, especially in terms of compliance, those changes will be applied on a yearly basis, that is counted here. And electricity price, we can here also see the the break-even fuel and electricity price with respects to the ship. So you can see that 21 or 22 cents is roughly per kilowatt hours is roughly the costs that a ship owner would have for this particular fuel price. So this is a way to see if the assumptions in the model also correlate with the ship owner, if that's applicable. So we're going to leave a little bit lower fuel price. There we go. Then we can directly see how that would impact, of course, the whole OPEX and thereby the business case. Also, we can change the EU ETS cost. That will of course drastically impact everything. Well, especially for larger ships, it can dramatically impact the total costs per day. Then we also have a little section on FuelEU Maritime with some more details. We calculate all the conventional and shore power savings. We can change the assumptions. I'll show you in the model. It is quite a biggie. In terms of formulas, etc. Many ways to splice and dice it. But what we basically do is that for each year we calculate the conventional greenhouse gas intensity and of course the greenhouse gas intensity including shore power, and thereby calculating all the penalties. We do not include any shore power penalties for not having shore power. That's simply not included because that really needs to be done on a case-by-case basis. If we need to incorporate it, should not be an issue, but it can be very hard to predict, well, for the individual ship. And of course, if we do that, then you'll see that you have an extremely positive business case because the penalties are tremendous. Then finally, we have the emissions calculated for when running conventionally on generators with idle mode and when on shore power. As you can see, this is with respect to the totals, so it includes also sailing. But in the model itself, you can have a closer look at what it means on the individual days. And also, I believe if we go here to ship fuel consumption, it's also, no, it's not hidden here. We could add it if needed. Well, I'm just showing it to you because all the types of calculations are included in the model, but we don't show everything because it is a lot already. And we'll then, I think, go to the model, except for one thing. We also include a feasibility study itself. So we have a blueprint for a feasibility study that you can use for internal use. And you can download that by clicking here. So if you click on the Word file, there you can see that you have everything you need to make a business case for yourself. That is it with respect to the web tool and how it works and how everything correlates. And now we'll go to the Excel model to show you how the calculations are done. And here she is. Don't be scared of the size or complexity. It's not too complicated. It's just a lot of calculations. A few general remarks that I've also noted here. Always make a copy first before you get started. Always also check values that you use, not just the prices, but the E-values for biofuels, should you use any. We only use one reference ship, as I stated before, and that's where all the calculations are based on. But make sure that you take the right example or just simply override all the different assumptions that we take, for example, for FuelEU, EU ETS, or the ship sizes itself. We have 53 of those ships available in the ship database, which I will show. FuelEU shore power penalties are excluded from this tool as of now. Could be included, just contact the help desk if you need those to include it. We calculate everything in euros, and also anything that's hidden, don't mind it. We didn't hide it because we didn't want you to find it, otherwise, well, you can always unhide stuff. But it's mostly there to make it simpler, more compact, or also help us with the web tool and other developments. So nothing to hide here, it's simply the fact that it's easier than for you. We also use a lot of named ranges that you can find here. If you go to formulas, named ranges, we have quite a lot because we refer to a lot of different stuff in the Excel sheet itself. That's just how we work. If you need help with the interpreting hereof, just let us know. The Excel sheet itself consists of the following tabs, and I will go through them a little bit, well, hopefully chronologically, so skip to the parts that you're interested in, but sometimes I skip a little bit in between because of course there's a lot of correlations. The instruction sheet that you know, input sheet, that's basically where you input all the data. It should be done well, only once, but when you have answers you go back and forth between input and output, most likely. Output is where we have 5 different outputs that should concern you mostly. Then we have power profiles, that's where we calculate energy demand of the ship, both regularly and on shore power. EU ETS and FuelEU calculations and rules. The prices data, that's, well, everything with data is a database, so those are, well, easier to explain. That's simply information of all the prices over time. Fuel data, same information about all the fuels. Ship data, what do you guess? Information about all the ships. SFC data, that's specific fuel curve. That's for the engines to determine the amount of fuel you will use under certain loads. And then we have shore side and ship side, and those are the more detailed calculations, as well as the CAPEX calculations for shore and ship side. Good to note as well that input cells, as you can see here, are highlighted in gray. Of course, you can change anything you want, but typically, especially in input, but also in a few other places, we show you these cells in gray. We've also noted a few things about EU ETS and FuelEU, and you can download our guides by clicking on the button. And of course, you can download the Word feasibility study template by clicking on the button. So let's get started with input first. The input sheet consists of a few different kinds of input. We have shore input, ship input, choose ship and ship specifics, some text there, operational input, amount of days, regulatory input, and then general input, mostly with costs, economics, etc. So let's go from top to bottom, and as you can see, everything is in column C, and we have some tooltips or explanations on different values and how we calculate them. Column E. So first, grid voltage, frequency, and E-house or grid outgoing voltage. You can see, well, this you can adjust to your specifications, a number, and we name them, as you can see here, all the way, typically with shore power shore or shore rated voltage going in or out. So here we typically assume that the outgoing voltage, as you can see, is equal to the rated voltage of all the shore power equipment. So we typically designate everything with shore and ship side. So the shore side equipment rated power in this case is 22 megawatts. And that's because, as you can see here, we take the rated power of the vessel and multiply it with a safety factor. But this is the rated power of the equipment on shore. The electric losses, that's incorporated in the power profile side. So we assume per item required a certain amount of electric losses. But of course, this totally depends on your system. And here we go. This is very important. Whether or not different converters, shore side, cable management system, transformers are required. As you can see, for a container ship we don't. So for all these categories we have included different tests in order to initially state whether or not those types of equipment are needed. And typically we simply take the voltage from shore and ship side for transformers, and if we need a converter, you'll probably always need to step down and up. So that's why if you have a converter, typically that should be true. The parasitic power demand, that's an important one for the OPEX. Typically a large installation requires a certain amount of power, even when it's off, maintain, have all the equipment on standby, etc. It can be a few percent of the regular power load when it's loaded. So this can really add up on the days that you don't provide any power in terms of costs. Then we have a terminal length, and then the different lengths of cabling from and to the E-house, as we call it. The E-house is where the transformer and the converters are stored, and of course the end of life of the installation. And then we have the ship. We can choose different ships, as you can see here. These are the ships that we allow you to choose, and if you change them, then all other information is changed as well. And you saw also that the assumptions that we assume for the ship also flow back upwards, or I should say upstream, towards the shore installation. So we're going to go back to a container ship. Override anything that you want. Also in terms of fuels, have a look and see which fuels we have available. We have quite a few. We haven't tested them all under each circumstances. Well, simply because most of them, or a lot of them, probably won't be used. So we didn't really bother to figure it out for everyone. If there's no need, then why bother? But they can be used anyway, and you have all the information in fuel data, which I will show later. And if you have a look here, then you can see that we typically use VLOOKUPs of either ship type, ship name, or etc. in the ship data table, and we match it with the name of the parameter that you see here. And if we can't find it, then we provide you with the input select ship. So basically what it does is we scan the database for that particular parameter, and we provide that specific cell as return, and we do it with this, well, you could say or argue, complicated formula. Is that because if you change any columns in the ship data table, then you still get these. So that's why we do it like this. Some more information. Again, this is not designated as an input cell because it takes it automatically, but you can override it, of course, wherever you want it. Then the main engine and the auxiliary engine. Yeah, as you can see here, we also assume certain set of parameters we take, but the main power is the total installed power. Have a good look, because sometimes, especially in this case, this could be total installed power for the propulsion, and this is of course total could be total installed auxiliary power, and then it all depends on how many engines you have. At the moment we don't really assume anything, we just take the total power demand and we take a certain specific load for it. But this is a key and critical component, of course, for any shore power terminal infrastructure, that you have a good look on the auxiliary engine and the power demand of the ship itself. The aux engine type and speed, these, and I will show that in the specific fuel curve data, SFC data, these will impact which specific fuel curve is used, and that correlates then from energy needs, fuel consumption for the ships. So that is always very important to have a good look at and ask the ship owner for their curves if they have one. Parasitic load, well, we have discussed that, that's a certain percentage, and here you can override the SFC curves, which I will show later, but then you can manually play around with the fuel consumption curves. LNG engine type, well, we have 1, 2 and 3, you can choose here. If you have an LNG engine, then you can choose between these different types of slip, also override that, of course. Then the rated power of the equipment, typically we take the auxiliary power as the rated power, but you can override that here. For example, if you have 18.5 megawatts of auxiliary power installed, maybe you only need 5 maximum in general cases. So you can override that value here, and everything that you see here we've already discussed in the web tool, so have a look, should speak for itself, especially with the explanation text here included. And then finally, important parameters, is it already ready for shore power? So does it include or exclude CAPEX and end of life? Then how we calculate the total amount of days. So what do? Typically we take simply 300 days per year sailing, and then the rest is idle moored. It really depends on your ship type. So have a look. I'm not sure if this fits. I'm pretty sure it doesn't fit you. It never fits anyone, a generalized assumption, but we gotta start somewhere. Then we assume 80% utilization generally. So if we have 300 days per year sailing, then we have 65 per days of the year idle moored. And if we have 80% utilization of the ship shore power, we have 52 days of shore power and then 13 days of idling and moored. You can see here that that's how we call these days: sailing days, shore power days, and idle moored days per year. And that's how we calculate all the different days. For each day we calculate OPEX, and then we multiply it with the amount of days to get you the yearly output. The shore infra supply days, or the shore power shore days per year, that is the amount of days that the shoreside infrastructure is actually connected to a ship of this size. So it doesn't have to be the same ship. What we say here is that this particular ship is connected 52 days per year, but the installation itself, like we showed in the web tool, can maybe provide energy to more and other ships, which will, well, improve its business case. What you notice is that if you only have 52 days that you can provide energy as a terminal owner or a port authority, then that's typically not enough uptake for you to make a positive business case. Here we also see something interesting. Sailing engine load of 50%, we're gonna make that 80% because, well, that should be roughly 80% as per EXI. But the average engine load here, that's for the auxiliary engine, idle moored engine load percentage. Yeah, as you can see, 39.5%, I'm simply 40%, which leads to an average resulting power of, as you can see here, 7.4 megawatts. So this is the average load, the average power, and as you will see in power profiles, that also results in a total amount of energy needed, of course, and also fuel needed. So these are critical input cells to consider. And again, if you have any trouble with them at all, give us a call. So here we have the reporting year. The reporting year is basically only important to, well, it's important for a lot of things, of course, but we calculate everything from 2025 to 2030, as you'll see in the output, and then the reporting year takes a specific slice of those years in order to get a representation of slice, especially in the web tool, you can see it easily. If you then change the reporting year, you can see the different years, how that impact mostly the compliance costs. So EU ETS average costs per metric ton of CO2, as you can see here, and global warming potential for methane and nitrous dioxide, N2O. So those are here taken from this source that you can find here. Can be updated and changed from time to time. And then finally, all the costs. What kind of cost do we have? Engine hours, of course, engine hour costs, consumables costs, generally, or the main. Typically, we don't take them into account from the start, but they could play a role, especially for well, if your engine costs are very high. Man-hour costs, both internally and externally. Feel free to change them. Then here you see we have generalized or taken assumptions on switchgear equipment, shore equipment purchase pricing, low and high voltage cables, and the cable management system in general. Well, these are again assumptions based on our experience with projects and the budget quotes and the quotes that we have received. Feel free to override them where possible. What happens is that in the CAPEX part of the different specific sites, those prices will simply be changed. So that's how that works. The same applies here, also in terms of maintenance of the shore power infrastructure on shore power maintenance per day, and also the shore power maintenance on board the vessel per day. We simply assume quite a high amount of maintenance. So have a look and ask your supplier of equipment if that also coincides with their experience. For the output graphs we include inflation and MPV discount rate, but general inflation on the OPEX is only considered for maintenance and spares, or any inflation on the monetary values for fuel that should be included in the fuel price. MPV discount rate, if you want a nice graph with MPVs, there you have it. And these are actually way more important, so maybe we should put them on top. These are the cost price of electricity for when the shore side buys the electricity, either from the grid or generates it or whatever, and then the electricity price as it sells it, and also how the ship buys it. So the electricity price is how the shoreside infrastructure sells it, ship buys it. And that's of course the magic number that we need to pinpoint exactly to get a good business case. The fuel price, of course, very important for the ship itself, its OPEX. Then we have the subsidy for shoreside infrastructure, subsidy for shipside infrastructure, and we also have a factor called ship attribution. We don't use it now at the moment, but basically what we did with ship attribution is we say, is it really fair to fully commercialize one shore power project of the ship for one terminal? Typically the ship goes to at least 2 ports from A to B, so maybe you could argue, well, half the money needs to be paid back. That's not what I meant. The investment needed for the shore power equipment needs to be paid back within a certain amount of year, but those investments might be cut in half, or like attributed only a certain percentage of those investments to this particular project. But you can simply override it by assuming a lower CAPEX or subsidy or any other way. So right now we don't use it much, but this is just here to keep you appraised of the fact that, well, maybe it's not entirely fair to attribute all the CAPEX of the ship to this particular project. And then finally we can also choose to do a financing. So instead of paying CAPEX for either the shore side or the ship side, we could maybe even do a loan or a lease, or what have you, for both of the sides, and then the interest rates and the loan periods are included here. So these are all the input values, and well, the input values apart from the VLOOKUPs for the ship side, those are basically, go through them once, input them, and then everything is run down to the different cells. Let's start with the output first. The output section consists of 5 different outputs. First we have all the operational profile outputs with some of the emissions and CAPEX for each operational profile. Then we have, zooming in, the average ship OPEX and the total amount of emissions per day. And here you can see we also have input buttons for whether or not you want to include that OPEX. Then we have the key output table that we use for making a key overview, especially for the web tool, but there we have the most important parameters neatly down, stacked in the middle. Then we have the CAPEX output table, that's the generalized CAPEX output table, where you can also include or exclude all the different cost components where needed. And then finally, and this is a biggie, as you can see here, the cash flow output table all the way to 2050. So for each year we have the cash flow at the ready. So we have that for shore side here, and we have that for ship side here. So you can use these tables to make graphs, calculations, representations, anything you want, and I'll quickly show them where everything is taken from. So in this case, and we're going to go to power profiles later on, we simply take the power profile of that day and we paste it here. So we calculate maximum power, average power, energy, engine hours, well, everything that you see here for each different operational profile. And we do that for both the conventional operations of the ship, so 300 days sailing and 65 days idle moored running on the auxiliary engines. And we do it for the shore power, so for 300 days sailing, 13 days idle moored, and 52 days running on shore power equipment. So we also include a measure if the shore power measure is not assumed. Well, of course we always assume a shore power measure here, but in our regular tools we can choose between the different options that we want. So we can either have shore power, we can have different kinds of shore power, we can do a lot of things. So if you see something like this, don't worry, simply look at the shore power days per year, or put in whatever value that you want here. And for the operational profile, we take an average. See here, why do we take an average day? Because, well, there's no average to be taken between sailing and idle. Those are totally different values, but that average day can be multiplied by 365 in order to get here the yearly outputs. So that's why we take an average. That's the reason for calculating the average sum product of the profiles that you see here. And the same applies to all the different vectors, including OPEX, although for OPEX we do have a look, see here, at the following, because we have all these different types of fuels that have prices per kilograms, liter and kilowatt hours. What we do is we again use a VLOOKUP to look at the fuel type that you use, then assume that it can be different from 2025 to 2050. I'll show you that. So each year can have a different fuel price. So we actually take fuel type at the fuel price rate of the reporting year that you provide. Then we have a look how it's described in euros per kilogram, liter or kilowatt hours, and then multiply that amount with amount that's been used according to the power profile. So that's quite tricky, but that's because, well, there's so many options, and this way you can just simply pick a fuel, pick a year, and then prices are calculated here. The same applies to financing, but for the conventional case we assume it's always zero, and shore power case we simply look at ship financing cost per day, which is calculated in the CAPEX part, which is in the ship side tab. Maintenance and also engine spares and consumables. Here you also see that we have prevent measures and change measures. Well, that's simply because when we have our regular tools, we also have different options, so that's where we include these kinds of variables. But for now, especially for shore power, as you can see here, we simply have shore power spares per day and also shore power maintenance. This formula above is simply taken that if you have 0 shore power days, you don't really in this case, but if you have it, then everything is neatly dashed and it looks better. So there's no reason in terms of calculating. EU ETS, well, we do the same here as we do above. We have a look at the total amount of kilograms in that particular case. This one's better. Or actually the tank to wake emissions. So here you saw well to wake. I've quickly changed it to tank to wake. Yeah, small error I didn't pick up, but that's because, well, we assume basically that there are no tank to wake emissions on shore power. That's how all the regulations assume, so I didn't double check that one. My apologies. So here we do the same. We take the reporting year, we look at the prices table for EUA, European Union allowance, and then we simply multiply the amount of kilograms tank to wake with the price of that year. Fuel use done totally differently. That's a whole different calculation, and that's done on a yearly basis, mirrored out of operational profiles. So that's it for the operational profiles. Then what do we do for the average? Well, then you see that here is where the averages are used. We take the average OPEX of the ship and we compare that with the average OPEX of the ship after shore power has been applied, and then you can see here the differences, whether or not you have a savings or not, and where those savings are included. And of course, if we include maintenance or financing, so if we make this true, then you can see, we can save a lot on maintenance. Well, make sure those values are correct, and then I can see how that impacts the bottom line. I'm going to leave that to false. There we go. And the same applies to ship emissions. So we take from the operational profiles here the conventional and the shore power emissions, and then we get these reductions, as you can see here. And mind you, this can look like only a little amount of savings, especially here when we look at sulfur and the particulate matters, but well, this is because we take it on a yearly basis. If you look on a daily basis, then of course then you have to, this is everything at 100%. It's not really fair to show that. So that's why we do it on a yearly basis. Then the key output table, this is simply taking all the most important parameters that are out there, but I'm gonna put this one and put it in gray. Not that I forgot, but this is a hard one, as in I don't know the payback rate that you assume for your investments. So we typically take 7, which is quite long, especially for a ship. But here you can change the payback required years, and then you can also see, let's see, if we take it to 5, then we kilowatt hour price need much lower in this case for the ship, because we have less time to make investment back, so we also need to pay less for the power. So the calculations made are shown here, the break-even prices. Let me just show you. We go all the way down here at the bottom of the output tables, and here we see again fuel, CAPEX, etc. What do? For the amount of years that we have, we calculate, or we combine all the costs. So basically life cycle costs. We determine the amount of kilowatt hours that have been used. We take the difference in what the maximum electricity costs would be compared to all the OPEX elements that you can see here. And then we have the total amount of kilowatt hours used while on shore power. And that's how we, divide it. We divide those two, and then we get a kilowatt hour price of the difference between, making money and losing money. And that's where we get a break-even price for both the ship. Well, this is done for the ship, and the same is done for the shore power infrastructure. So basically calculating all the kilowatt hours within the time frame that you have provided, and then dividing that, dividing the monetary value with that amount of kilowatt hours. So that's how we calculate these payback rates. The payback year, as you can see here, those are simply calculated by taking it, looking at the time when there's a break-even point in the graph, and then it's also calculated into years, payback time in a year, so 2 years and 6 years. And that's the key output table. So, well, the key output table in terms of CAPEX, this is simply looking at the CAPEX costs of the shore side and collecting that specific node of information. We also add additional equipment there, and then of course design engineering, installation and class, and subsidies and needed. But these are simply collected, so if you change anything here, stuff breaks. So do that at the input or the CAPEX side. And here for each year we simply calculate everything per operational loads, per operational day. So that's an important one to have a look at afterwards. We simply take an index of the shore power profile. In this case, if we have electricity, for example, with kilowatt hours of that particular power profile, multiplied with the amount of days, and that's it. And we also add the cost for the shore power parasitic load, of course the costs for generating electricity when it's off in the non-shore power days. And here, if you have a close look, we do that for each year, so the prices for those years will be multiplied with whatever you, with the power profiles, but whatever you have in terms of prices, that will be automatically assumed here. The same applies for everything, also in terms of CAPEX of the ship, costs elements. What we do here is we calculate it before and after, and here we calculate the cost without electricity in order to calculate the break-even price. And everything is put together in a result, cumulative MPV, and if needed, the principal payment, interest, and payments per year if you have a financing option. So that is it in terms of the output. It's it's a lot, but luckily the output is simply collecting information from all different aspects. For the most part, let's go to power profiles. That's an important one. And it's important, but luckily it's also, brief. We have 3 different power profiles: the regular sailing, the regular idle moored on generator, and when on shore power. For each of those power profiles, we calculate the maximum power, the average power in kilowatts, the energy required, so that's 24 times the average power, the amount of engine hours for costs, the average specific fuel curve in order to derive the fuel consumption in kilograms, liters and kilowatt hours. And here it's empty. You think, hey, hold on, what's there? Here you go. So this is for each day. So we calculate for each day consecutively per 10 minutes what the power demand is and calculate or transform that into a fuel consumption. And this is where you can include your own power profile of your ship, so see how your power profile would directly impact all the different CAPEX. So that's where you do it. So basically we take all the operational days, we see the energy demand, the kilowatt hours per 10 minutes, and then we transform that in amount of energy per day and thus fuel per day, specific fuel curve. And that's something I'll show you almost all the way in the end. So moving on to EU ETS. EU ETS, well, it has a lot of rules, as you can see here. For each year, we typically look at what the EU ETS impact is on your ship type and vessel, but rest assured, basically it's the amount of kilograms tank to wake of emissions that will be multiplied with the prices of that particular EU ETS price or EUA price, European Union allowance price per day. So you can see that we take the average amount of CO2 emissions in kilograms daily divided by 1,000 metric tons, multiplied by the amount of years, and also whether or not we want to include the OPEX of the EU ETS, and then simply multiply the amount of tons per year with the price of the European allowance. That is what we do here, nothing fancy much. Moving on to FuelEU, which is a total different animal. FuelEU is granted pretty tricky. We actually have whole different tools for that. So if you need specific assistance on FuelEU, we can give it to you. But what we do is we have the FuelEU calculations, current output table for the current situation, current meaning conventional. And then we have the FuelEU future output situation for shore power. And for each year we determine the amount of fuel, main and auxiliary. And this is also why I keep on stressing how important it is to have the sailing and the auxiliary amount of fuel included, because these both will transform into an amount of penalties or not. We also take the amount of electricity consumed by shore power each year, as you can see here. So that is simply the amount of days multiplied with the amount of kilowatt hours transformed into megajoules, and then we calculate greenhouse gas intensities, targets, compliance balances, etc. We also have the option to include a penalty and multiplier, but typically I'd say it's complicated enough, so leave that closed. Simply look here, the FuelEU penalty per year, and then the FuelEU penalty conventional per year, left right there. And that is what we compare these two. So we have the FuelEU output, we calculate greenhouse gas intensities and calculate penalties, and then the difference you save per year. And that is why it is so hard to really put a penalty per day on a shore power day, because, well, sure, you can say without shore power you don't have those savings, but really the mix of the main fuel and auxiliary fuel is very important to calculate the greenhouse gas intensity of the ship. That's all stated here. We have a nice guide that you can have a look at. And what else do we do? These tables are simply for calculating, well, penalties and targets. And here we have the key output table that you also saw in the web tool. This one, it might be easiest to see that for each year, what do you pay conventionally, what do you pay for shore power, and then save. What you can do is you can override the main fuel consumptions here if you only want to have a look at main fuel consumptions with respect to FuelEU. But what we do is we take the outputs, we take the values from the outputs. So that's why I go from left to right, because every time we override some stuff, the stuff before is not overwritten, and it could lead to errors later on. You have different inputs at different places. So FuelEU is quite tricky. Contact us if you need any help there at all. Now we get to the more easier parts. These are simply tables. So what do we have? We have prices of all the different fuels and electricity used. We have the units per kilogram or meters per kilogram or liters. Here you can also see that exact unit on that particular year, but for each year we have simply taken, well, the starting value. So we leave it up to you to change it however you want. We have done scenario modeling, ups and downs, etc., but you know, things are complicated enough as it is. Right now, this is your way of incorporating the prices that you want to do for, you know, whatever you want to do. The prices in gray here, those are biofuels. So we have regular fossil fuels, biofuels, and then RFNBOs, renewable fuels of non-biological origin, all the e-fuels you could say, and of course the electricity. So this is fossil, bio, and electricity based generally. For fuel data, well, hey, that looks familiar because it is. Here you see we have all the different values of the fuels listed. So these gray ones, by the way, are not input values. Basically everything is an input value, but if you don't really have the distinction between biofuels, fossil and RFNBO, it can be a bit complicated. Change anything you want here. We've taken many things from, as you can see here in the sources and the tooltips, the FuelEU regulations, also the remainder of the biofuels where possible, and in RFNBOs, but many are unknown. So a lot of parameters, especially with respects to E values, they can change. Tank to wake values for RFM can be very different on the types of engines. So this is something I definitely have a look at if you have different values or other values that you use biofuels, because that can really make a big difference. Yeah, that's why always double check it. Moving on to ship data. So here we have ship data. It's a lot, but let's zoom in. What do? So we typically start with a ship type. So here we have all different ship types with an IMO number. Well, basically we took the liberty of looking up specific ship types that we think are representative, and we've simply taken 53 of these different ship types and given you the opportunity to simply pick and choose whichever suits your vessel best. But you can always, of course, override that, not just here, but also in the input value. Make sure that if you override it in the input values, the links are broken, so the VLOOKUPs in this table won't work anymore, and you cannot simply click on ship name and then you get all the info listed here. That's fine, so always make a copy. What you can also do is you can input your own vessels here, so that you can do your IMO number, your ship type, ship name, etc. And then all the information for your ship is loaded in. Make sure that if you do so, ship category, the FuelEU and EU rules are typically per ship category. So if you change this to something else, that might break there as well. So keep these categories if you want to have that stay the same. Apart from that, ship data, well, that's simply a nice database. SFC data, the next one. So what do we do here? This is an important column B. So from 0 to 106%. That's the engine. So this is a diesel engine from 0% load to 106% load, overloaded. And then we calculate specific fuel curves in different ways. The source can be found here. That's where we explain everything on how we calculate it. But basically the curve itself is simply the load curve of a diesel engine. And here you see the resulting engine curves, specific fuel curves for the main and auxiliary engine from 0 to, let's see, all the way 106% load. And that's why if you change the stroke of the engine and speed of the engine, that will impact the curve. But if you have your own engine curves, you can simply input them here, and then all the values will be accordingly. So if you have anything in terms of an engine curve for your main and auxiliary engine, then you can put that here. So now let's move to the two last tabs, the shore side and the ship side, and these are again a little bit more elaborative. They are more elaborative, but they are also closely alike. So if we zoom out, what we have for both shore side and ship side, we have on the left hand side more technical details, lovely, especially on equipment and power transformers. In the middle we have output per operational profile that you see here, output for different operational profiles. Here we have again information on operational profiles themselves. In the future we'll probably remove them because it's a little bit double, but here you can see per operational profile how it would affect the ship side, and we have the same for the shore side that we have here. But the shore side also simply includes selling electricity days and not selling electricity days, simply having costs, well, for now. And then we have the CAPEX that we have here on the ship side, and that's where I want to start because, well, everything here has already been discussed. The very technical aspects, especially on the ship sides, are explained here, What we do is we simply calculate for all the types and equipment, sockets and plugs, what's required based on your input. So these can be directly given to a supplier in order for them to get a good reference of the kind of equipment that they need to build. And of course they can ask you questions about it. But this, the CAPEX side of things, that's of course a lot more important than those nitty-gritty details. So what do we do here? We simply calculate or sum the amount of time required for all those different elements, and we multiply it with the amount, well, we don't multiply, we multiply it here, of course, man hour external or internal, so we multiply the man hours with the amount of cost. And at equipment procurement, here we go, we see that based on the technical input that you provide, and of course based on the economic input that you provide, we simply calculate the costs for each different line item. So we have the work that needs to be done with a certain amount of cost, and we have the retrofitting, commissioning, class and certification, also work that needs to be done, plus the equipment that to buy. And basically looking through these different cells, you see that we go to output, the true false boxes, we multiply it with the amount of shore connection panels. As you can see here, each shore connection panel has a certain equipment purchase price that we did in the input values, and then we get the total cost. So that's how we build up the entire sheet. And everything is summed here, and these values are then used, or this entire table is then used for the CAPEX cost in the beginning. And the CAPEX for the shore side works, well, exactly the same. We have different line items, but we have this kind of space. We have design, equipment, installation, so that's how the CAPEX is built up based on your input. The operational profiles we have already discussed for those operational days, resulting in the key averages that you see here. And this we simply take only here, because as you saw in the output, we calculate everything per year. So this is the output per day for the ship specifically, but again, because it's the same information spliced differently, we're probably gonna remove that later on. So one thing to note, as I said, we have for the shore power installation standby and providing shore power. Well, basically we do that to calculate, of course, the OPEX cost, so that's a bit different ship side, but any different kinds of operational profile could be added here, and we make sure that the different costs for each day are correctly included as well. And that's it in terms of the Excel sheet. We're done. And there's only one more thing left to say from our side. If you have any questions at all, contact the help desk, give us an email, schedule a call to make your life easier. We provide you all the tools to do it yourself, but sometimes you just need a little help. So feel free to reach out. Thanks for watching the video and have a great day.